Uh, Earth calling Thermo students. Earth calling Thermo students. Come in, Thermo students. Hello out there in Thermo listening land. Let's see if anybody's shown up. Nope, nobody's shown up yet. They're taking naps. They're taking afternoon naps. That's what they're doing. Well, that's okay. They can take a nap. We, I believe, got started on 9:13. So that's what we're going to work on. Nobody showed up yet. Hey, Abdullah. Abdullah just showed up and Kristen showed up. Great. We have three of us now, including me. Good deal. Hello there, Thermo students.
Hello.
Hello.
Okay, I will be right back. I'm gonna back in a few minutes. I just wanted to get my computer all loaded up so I wouldn't be late.
Great. We're on time. We're doing fine.
Yeah, a few minutes early.
Yeah.
Thank you.
Thank you. Now, what if I go up here and click on Abdullah? What happens? Nothing. Nothing happens. What if I click unmute on Abdullah? I just clicked on unmute. What do these three dots stand for? It says,
It's just asking me if I want to unmute or not.
oh, okay. Good to hear from you, Abdullah.
Thank you.
Well, we only have just a few students, so we'll wait for a while, but we're going to study this 913. This is problem 913. Abdullah, you're listening. This problem 913. Didn't we get started on that Monday?
Yeah, we did, but we did not finish it.
Yeah. I told you to go home and finish it. Did you get to finish it?
I tried, but I did not. No.
Well, that's okay. We're going to go through it.
Okay.
We're going to go through it and try to answer all your questions.
All
But
right.
before we do, did you have any comment or question?
Yeah. So, are we having a test and a final, or just a final?
No, we are having just a final.
Okay. Okay.
But see,
And that final will count for both the test and the final?
well, it will replace your lowest grade. So it could count twice is what it amounts to.
Okay.
That includes your homework grade, but I'm sure your homework grade is good. Well, I'm sure you've got good grades on everything, so it
All right.
might not count twice for you, but for some people it could count twice. If they have a
Okay.
low grade, we'll replace it with a final.
All right.
Well, hey, we got some more customers. There's Kerman and Kristen and Jackson. Good, 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 good. We have some more people coming in. While you guys are coming in, I'll ask you some questions here. This particular kind of cycle here, it's not a diesel cycle. What is it? What's the name of it? It's a particular kind of cycle. It's a type of power cycle, but exactly what is the name of this cycle? I'll pick on somebody in particular. How about my friend Abdullah? We were just talking. Abdullah, what's the name of this cycle on problem 913?
Um, let me check my notes.
I'll give you a hint. It's the cycle that generates electricity, not only in the United States, but as far as I know, around the world.
Um,
Europe for sure. And I'll give you a hint. It starts with R. Starts with R.
I'm not.
Well,
I'm
that's
not sure,
okay.
honestly.
That's why you're here. You want to learn this. But we should know the name of this kind of cycle. See, we're going to study different cycles. We're going to study refrigeration cycle in detail and diesel cycles. I would say diesel cycles are important to us. Aren't there big diesel trucks bringing the food to our grocery stores right now? You guys
Yep.
like to eat, right? You like to
Yeah.
eat? Yeah. Well, the diesel cycle is pretty important because those are diesel trucks. And the farmers that grow our food, they have tractors. And guess what? They're diesel tractors, aren't they? So we'll study
Yep.
the diesel cycle, but this is not a diesel cycle. I'll pick on somebody else. Hey, Levi just showed up. Levi, unmute and tell us the name of this cycle on problem 913. Go ahead, Levi. I'm listening.
Isn't that a Rankine cycle?
That's it. Good going, Levi. Here, let's write that down. This is a Rankine cycle. And this is the way electricity is generated in the United States. Now, the Rankine cycle consists of 4 processes. This one here, this 3 to 4, on a TS diagram goes straight down. It's what they call an isentropic constant entropy process. And that's in the turbine. Now you got to understand something. This is an ideal Rankine cycle. In an actual real world Rankine cycle, you'll have some irreversibilities, and this process from 3 to 4 will be a dashed line, and it'll hang over here and go off to the right a little bit because it won't strictly be an isentrope. Does anybody remember what an isentrope is? Let me write that down. I'm quizzing you guys on some basics here. An isentrope, let's pick on Kerman. Unmute and tell me what, Kerman, tell me what an isentrope is. Earth calling Kerman. Come in, Kerman. Well, he's not coming in. Kerman, unmute. Tell me what an isentrope is. He's busy doing something else. Maybe he's fixing his coffee or something. That's okay. Well, if he won't tell me, I'll tell you. What an isentrope is when your entropy at, well, in this case, it's state 3, is equal to the entropy. I probably should write little letters there. The entropy at state 3 is equal to the entropy at state 4. That's what an isentrope is. It's constant entropy. I want you to look at little s at state 3 and little s at state 4. Oh, look, they're the same. The reason why they're the same is this is an isentrope. It's a constant entropy process. That's a turbine. Well, it's an ideal turbine. The actual turbine won't be ideal, but we're studying the ideal Rankine cycle. Okay, well, let me ask you some other stuff here. Hey, it's 1 o'clock. That's enough asking stuff. Let's move into what we're going to talk about. What I thought I could do here is go over each one of these boxes and show you where the numbers came from. Okay. Now this is problem 913. And we're going to go through each box here and show you where it came from. We'll bore you out of your gourds. It says here a steam power plant should produce 10 megawatts of net work. Well, that 10 megawatts doesn't go into any of these boxes. Now they do have the net work per mass right here. You know, you see this number right here? That's little w. That's the net work per mass. And it's in kilojoules per kilogram. But that is not the power. This says the power is 10 megawatts. Here's the equation. It goes like this. Big W dot is equal to M dot times little w. They said that the power, the net power of this cycle is 10 megawatts. Do not confuse that W with that W there. That's a unit. This is an algebraic symbol. Now, we're not supposed to know what that little w is, but see, if we're talking the net power, and this is the net work per mass, I got the answer. We figured it out. We're going to go over these boxes here, and I was just going to show you this. See, you can solve this and get your mass flow rate. All right, get your calculators out and solve that for the mass flow rate. Here we go. You got to be careful about your units. Okay, I got an answer. And I think that's correct. Let me check here. I don't want to lie to you if I can help it. No, that's correct. That's the mass flow rate. They asked for it. I think. Did they? Yeah, they asked for the mass flow rate. Well, that's the mass flow rate. Does anyone need me to explain how I did that and got m dot? I'll be glad to. Okay. Nobody asked me, so I think you can do it. All right, well, let me keep reading on here. I'm reading what the problem is. We're talking about 913. It's a Rankine cycle. And they said steam flows at 5 megapascals, 500 C to the turbine. Okay, now this is the turbine. And this steam right here is at 5 megapascals and 500 C. Well, that's state 3. Look, state 3. See, we put the initial, these are all the initial properties for this process. Going from 3 to 4, the initial property is at 3. The final property will be at 4. But at state 3, we have 5,000 kilopascals. Well, they said 5 megapascals, but it's the same thing. And it's 500 degrees Celsius. So what I'm going to do is I'm going to circle the numbers that I'm showing you where they came from. These numbers here came from reading the problem. They said it's 5 megapascals and 500 Celsius. So that's where we got those numbers. Now this number here, you can't get it from the ideal gas law. I'm sorry. This stuff is H2O. Do not use the ideal gas law on H2O. Use the tables. So go with me to the tables and we're going to look up. Now, which table do you use? Well, we're doing state 3, so you have to use the superheated vapor table. So go to the superheated vapor table. I'm looking here, superheated vapor, trying to find the water here. Okay, hey, I think I found it. Oh, nope, I need superheated. Haven't found that yet. Still looking. Superheated water, there we go. And we need 5,000 kilopascals. There it is, right? Hey, I finally found it. I found the 5,000 kilopascals. Now I'm going to look at 500 Celsius, and I found that. Hey, there's your specific volume right in the table. It's 06857. If you have a table like I do, I'm looking at it. It's in the table. It's 0.06857. That's where we got this number. Can you find it in your table? I hope so. See, this is really pretty easy. Just look that stuff up. Now, if you want the specific enthalpy, we can just look that up. Go to this 5,000. I got lost. There it is. Look up 500 Celsius. This says 3433.76. Well, there it is, 3433.76, right off the table. So let me circle that. See, here's what we're going to do. We're going to circle every box on here because I'm showing you where it came from. Now, for the specific entropy, it's 6.9758. Look here, 6.9758. I'm going to circle it now. I just read it in my table. You can read it in your table. Okay, good. We got that. Well, let me go back to the problem and read it and see what it says. It says here, the condenser operates at 50 degrees Celsius. All right. Condenser. This is the condenser, guys. When you go this way, you're condensing. And when you go the other way, you're boiling, or some people call it evaporating. It's the same thing. You're evaporating and going to the right, condensing going to the left. And they said it's at 50 degrees Celsius. Now, this is one of the things you can count on a Rankine cycle, in that the pump starts at saturated liquid. Remember, this line is saturated liquid. And so we're going to look up 50 degrees Celsius saturated liquid. Go with me to 50 degrees Celsius saturated liquid. I found it. Okay. We're looking at state 1 now. And it says here at state 1, 50 degrees Celsius, the pressure is 12.35. 12.35 kilopascals. I just read it off of my table. I hope I'm boring you because this is so easy. See, these will be worth a point apiece on your final exam. And we're just going to fill them all in. How many are there? 1, 2, 3, 4, 5, 6, 7 times 4. Well, that's 28. But if you miss one of them, you'll lose a point. Okay, now we're going to read the specific volume at state 1. Well, at 50 degrees Celsius, it says 0.001012. Well, there it is, 0.001012. We got that. Just read it off the table. Hey, we got some more people. Tyler came in, and Mark, Levi, Coy is all there. All right, 50 degrees Celsius. Well, that was given. That's given in the problem. What does it mean in this class when I circle something?
That we know it.
We know it. Well, that was just given in the problem. And I'm showing you where I'm getting each one of these numbers. Okay, now this one here, we just look it up. 50 degrees Celsius. I'm in the saturated table now. And it says the little h is 209.31. Oh, there it is, 209.31. What could be easier than that? The little s at 50 degrees Celsius, if you have a table. Now, if you don't have a table, you don't know where I'm getting these numbers. But the little s is 0.7037. Well, there it is, 0.7037. We're coming right along. Now here, let me show you the dirty little secret of the Rankine cycle. These two numbers have to be the same because the pump going from 1 to 2 is an isentropic process, constant entropy. And the turbine going from 3 to 4 is an isentropic process, constant entropy. So we got all those. Now let's go to maybe state 2, shall we? See, what I'm doing here is I'm putting in the first one. I'm putting in, this is state 1, this is state 2, this is state 3, this will be state 4. All right, let's do state 2. Now, state 2 is right here. That's compressed liquid. So we're going to go to the compressed liquid table. flip with me. Help me find the compressed liquid table. Compressed liquid table. And we want 5,000 kilopascal. Hey, there it is, 5,000 kilopascal. That's given, isn't it? Yeah. Yeah. Do you remember at state 3, we have 5,000 kilopascals? Well, from 2 to 3 is an isobar. It's constant pressure from 2 to 3. Look at here. If state 3 is 5,000 kilopascals, then state 2 is 5,000 kilopascals, but it's in compressed liquid. So we're just going to look it up. What's it say? Now here's a problem. We need the entropy to be 0.7037. Uh-oh. They don't have a 0.7037. We're going to have to interpolate. All right, well, let's interpolate. I'll say goodbye to this stuff here. Now what we have here at 5,000 kilopascals, I'm going to write this, that we're going to have T, V, H, and S. We have a 40. We have 0.001006. We have 171.95. And we have 0.5705. This is tedious and boring, but there's things in life that are tedious and boring. You know, doing dishes, for instance, changing diapers. You know the drill. And this here is 0.001015. And this one's 255.28. I'm getting these off of the table here. The compressed liquid table for water at 5,000 kilopascals, and this one's 0.8284. Now, see what we want is 0.7037. We want 0.7037. So we have to interpolate. I won't bore you with the interpolation, but I'll just put the answers in there, okay? But if you want me to go through any one of these, just tell me. All right, this is going to be 50.3 when you interpolate it. This one's 0.001008. Hope you can read that. This is 214.99. 214.99, and of course that one's 0.7037. We know that's right there. We're going from 1 to 2. Okay, well look, we just got our answers, and that's where the 0.001008 came from. We interpolated. And look at this 214.99. That's where that came from. We interpolated. So we just figured this out. And the 50.3, we interpolated. That's where that came from. And that's where that came. Hey, we're making progress. Look at us. What do we got left? This line down here? Okay. But let me pause and let you mull that over and give you time to ask me anything that's bugging you. It's really easy. It's just a matter of tedious, boring work. We got some other customers here. We have our friend Tyler, Mark, Levi, Kristen, Coy, Kerman, Jackson, Ethan. Yeah, Ethan's here. Daniel, Brandon, Abdullah, and Ross. Ross is there too. Anybody have a question or comment before we need to get these numbers here. Okay, well, nobody said anything. Let's do that. Now, state four, I tell you what we know. We know this entropy because 3 to 4 is an isentropic process. So we know this. And we also know the temperature. They told us that in the problem. They said it was 50 degrees Celsius. If you go to your table and look up 50 degrees Celsius, you'll get the saturation pressure. It's 1235. See, it's 1235 at state 1, but it's also 1235 kilopascals at state 4. But we got two boxes here to fill in, and we're at state 4, and we need this specific volume. Okay, well, we can do that. All right, how are we going to do that? Well, I need to get rid of this because we're no longer at 5,000 kilopascals. Let me get rid of this, and we're going to work on these two. What's that 60 doing? Oh, that was, we were interpolating, yeah. Whoops, I didn't mean to erase that. That's state 3. Okay, we're going to go to state 4 now. Hey, you know what? State 4 is what they call saturated mixture. And here's what we're going to do. We know the entropy, specific entropy of state 4. It's the same as it was at 3. It's 6.9758. And that's going to equal little sf plus the quality at state 4 times little sfg. See, we can look these up in the table. We know what this is, and we can look that up, and we can get the quality. Here, let me write the numbers for you. Go to 50 degrees Celsius with me. I'm shopping around here trying to find 50 degrees Celsius. Aha, I found it. Okay, now we already know what this has got to be. It's got to be 6.9758. We're going to look this up at 50 degrees Celsius. And here's what it says in my table. It says 0.7037, 0.7037. And this right here, what that is subtracting SG minus SF, and it's 7.3725. And now we got a lovely equation with one unknown. We can find the quality at state 4. Quality. It'd be nice for you to know what quality is. I'm going to ask one of my wonderful students here what quality is. Let's see. There's Brandon. Brandon's a wonderful student. Brandon, unmute and tell the crowd what quality is. What is it? Earth calling Brandon. Earth calling Brandon. Come in, Brandon. He's not going to come in.
Is it quality of mixture? So you have like 50% water, 50% saturated vapor or something like that?
Exactly. Exactly, Brandon. Now, don't go away, Brandon. I'm going to get this number here. The quality, if you solve that, is 0.8507. What that stands for, Brandon, is it's 85% something. But here it is, 85% what? It's state 4.
At state 4, it should be 85%. I think it's steam and then 15% water.
No, 85 doesn't add up to 50 and give 100. That doesn't quite work that way. Now 85 and
No, I said 15.
oh, did you say
1-5.
50? Did you say 50? Yeah,
15. Yeah.
my fault. You did say 15. Yeah, it's 85% one thing and 15% the other. But which is which? 85% what, Brandon?
It should be a higher percentage of vapor.
Got it. Yay, Brandon understands quality. What it is, quality, he understands. What quality is the percent vapor that you have. Now, we have 85% vapor at state 4. It's mostly vapor, but it's around 15% liquid. You still have some liquid. And I'll tell you something about turbines. That liquid is little drops, and they're going very fast, and they hit those delicate turbine blades in your turbine. See, this is a turbine, and those are little liquid drops, and it's just like hammering that blade, and they break off sometimes. If enough drops hits that turbine for a long enough time, it will damage the turbine blade. You've seen turbines, they got all hundreds of these little blades on them. And if one of those blades gets knocked off, guess what? It's out of balance. You don't want that turbine to be out of balance. It'll start to vibrate, won't it? You'll have big problems. So what do? They shut that turbine down, but they have a spare turbine. They have 2 turbines at the power plant. If you go to the power plant, they have 2 turbines. When they shut the one down, they got the other one all ready to go, and they fire the other one up, and you still have your lights on. You still have electricity. That's kind of interesting, I think. Yeah, there's jobs out there. There's people that work in these power plants. I don't know if you've ever been awake at the middle of the night when something weird happens. The lights, they go off for just a second, and then they come back on. I wonder if that's ever happened to any of you. You know what they were doing? They were switching the turbine. They switched the turbine. By the way, those turbines spin in the United States at 60 cycle, 60 revolutions per second, I believe. Yeah, 60 hertz. It turns 60 revolutions, that the turbine blades, the turbine turns 60 times per second. In Europe, it's 50 times per second on their turbines. Okay, well, let's see. How are we doing now? We figured out the quality, and now we can get these last 2 boxes. Let's get those. All right, I just need a little room to work here. If you want this little V4, it's going to be VF plus your quality at state 4 times VFG. And we know what VF is if you look it up at 50 Celsius. I'm doing that now. That's 0.00112. Wonder if I did that right. Yeah. Plus the quality, which is 0.8507 times 120308. 12.0308. Now, if you plug that into your computer, and you're very lucky, you will get 10.236. Let me do it and see if I'm lying to you. I'm plugging that in right now. Boy, Jove, I'm getting 10.236. Hey, we just figured out where that came from. I just showed you where it came from. Hey, we got this box to do now. Let's do it. Well, to do that box, you go H4 equals HF plus the quality times HFG. Okay. Let me look those up and we'll do that one. But first, is there any comment or question bothering anybody before we do that? I'll tell you a little secret about the Rankine cycle. If they could get this just a little hotter, if they could get this a little hotter and bring this up, see, this is an isobar. Going from 2 to 3 is an isobar. The whole thing is an isobar. If they could get this just a little hotter, hotter, and then when they came down here, ding, can you see that they could get rid of those water drops and they could get 100% vapor and they wouldn't wear out the delicate turbine blades? Now, how are they going to get that hotter? Well, you could read your chapter, they tell you, but they're burning coal, okay? And let me make a little room here and then we'll get that last thing here together. You don't need any of that. You understood all that. I don't know if you've ever looked at a candle flame, but a candle flame, it sort of has a blue inner core here that kind of goes up like, go get a candle sometime. And this other part is more of a yellow color. Look at a candle carefully sometime. Do you know where the hottest part of that candle flame is? Let me ask somebody. Let's go to my friend Ethan. Ethan, I never bug you. Ethan, unmute and tell me where the hottest part of that candle flame is.
Inside.
Yeah, it's inside. It's not up here, Ethan. The hottest part is right there. That's the very hottest part of your candle flame, right above that blue thing inside your candle flame. And what they do is they run the pipes with this steam in it. See, out here you got steam. There's no liquid at all in here. This stuff out in here is superheated vapor. And they run the pipes carrying that steam over the hottest part of, you're burning coal. It's not a candle, it's coal they're burning. But it has a hottest part just like the candle does. They run that, and they're able to get it hotter. That's the dirty little secret for getting it hotter. And then you get a quality that's bigger, or maybe 100%. So there, we've just explained that. Back to our problem. We told you about the candle there. Let's get the enthalpy. This is specific enthalpy, and we're going to do it now. We're going to get H4. It should be at go to 5,000 kilopascals. I got to do a little digging here now. I know this is boring and tedious, but so is changing diapers. But it's important. It's especially important to the one that you're changing the diapers on. Okay, go to 5,000 kilopascals. I found it. Superheated vapor water. And what we want is 500 Celsius. And here's the H. No, I got mixed up, guys. Forget everything I just said. We're trying to find state 4. So what we want is 50 Celsius. I don't know, something happened. Senior moment. I had a senior moment. But I'm back on track now. Go to 50 degrees Celsius in your table and look up HF, which is 209.31. And the quality is 0.8507. HFG is 2382.75. And do that, you should get 2236.4. I'm going to make sure. I'm going to do it. You do it. And I'm going to do it. On your mark, get set, go. Well, I did that. Here's what I'm getting. I'm getting the specific enthalpy at state 4 is 2236.3. Well, that's what we got. Look, we just showed you how we got that number now. Each one of these will be worth a point on your final. Now we need to show you where those numbers come from. But first, did anybody have any question on any of that?
Yes, sir.
You're okay. All right. Well, the reason why these heat transfer per mass are 0 is those are adiabats. See, 1 to 2 is an adiabat, 3 to 4 is an adiabat. Now going from 2 to 3, there's no work done. Boilers don't do any work. They don't do any work. Let me see if I can explain that. How come they don't do any work? If you did a PV diagram, of this Rankine cycle, here's what it would look like. You would have, that was kind of messy there. You would have a condenser doing that. And then you would have a pump. Pumps are constant volume, they're liquids. Did you know liquids don't, they don't compress very much. They're kind of like solids. They might compress a little, so do solids a little, but basically liquids are incompressible. So you got an isochore there to state 2. Here's state 1, here's state 2. And then what happens? Well, you've got an isobar. Remember, from 2 to 3 is an isobar. Well, on a PV diagram, it goes like this. It goes, it goes straight across. Actually, this probably has to go up higher. That has to go up higher. There you go. It goes straight across because it's an isobar, and we're doing a PV diagram. And then from 3 to 4, what did we say 3 to 4 was? That's a turbine. That's not an isobar or isochore. No, it goes like this. There's state 3, and here's, sorry, it's kind of messy, but I'm doing the best I can. Here's your state 4. That's what your PV diagram would look like. And I bet some of you did that. I bet some of you did that PV diagram. See, we could even label it. This pressure here is 5,000, or you could say 5 megapascals. This pressure here is 12.35 kilopascals. And we could label it some more, but that's good enough. But here's what I want to show you. Do you remember, if you got a control volume, which is what we have, this is not a control mass, this is a control volume. The work, and how much room to write here? Let me get rid of that. I need some room to write. It's kind of a fascinating little tidbit here for you. Hope you can read my writing. That's supposed to say state 3 right there. The work per mass on a control volume, if you do it, it's equal to VDP. It's not PDV. See, on a control mass, the work per mass is the integral of PDV. You guys are all happy with that and familiar with that. See, that's the area underneath your diagram. But see, you know what this is? It's the area sideways. I was telling you guys about that last time, I think. Well, what's the area under this line right here? There isn't any. Now it's got an area underneath it, but this is a control volume. So the work done per mass going from 2 to 3 is 0. You see that 0? Going from 2 to 3, the work's done is 0. Now going from 4 to 1, here's from 4 to 1. See, we're looking at this right here. We're looking at the integral of VDP. and you get 0 because it's the area sideways. I drew a picture for you the other day. It's in your book too. Now, let me see if I can find it in your book. Does anybody know what page that was on in your book that I showed you about? Probably don't know what I'm talking about. Maybe I can find it here. It would be getting warmish here. Yeah, here it is. Look on page 218. Look on page 218 if you have a book. And you'll see they have a PV diagram. And they're looking at the area, not underneath, below, but sideways. Well, there isn't any area sideways on this here from 2 to 3 or from 4 to 1. If you look on page 218, it explains it better. And you'll see that equation right there on page 2, at the bottom of page 217, only I wrote it wrong. It's got a minus in front of it. Somebody could have gotten a thank you point for that. You'll find that equation right there on page 217. Well, I'll pause in case anybody wants to say anything, and then we're gonna finish those. How are we doing on time? Well, we're having fun, right? Now, I gave you some homework that I'm going to grade, and it's in Blackboard under assessment, assignment. Go to Blackboard, and then you click on assessment, click on assignments, and I gave you some homework. I'll talk about it in a little bit. Now, I just don't know where I'm at with you guys, whether this was worth doing. It's tedious and boring, I know that much. But I'd like you to do good when you have this on your test, and this is how you do it. Okay, now let's get these numbers here now. Here goes. I just need some room to operate here. Let me get rid of all this stuff. Nobody asked me any questions. I gotta find out if anybody's really out there. Let me go to my friend Levi. Unmute and say hi. Levi.
Hello?
Hey, hello, you're there. Good.
Yes, I'm here, of course.
Yay, wonderful. See, I like the feedback. I like the live people. I don't like this. I feel like I'm talking to a microphone. That's okay. This wasn't our choice. We're just doing what we have to do. Okay, well, let's get this little W right here. Here we go. Now, the way to do that is you write your first law of thermodynamics. But since it's a control volume, see, mass comes in these devices and mass goes out. It's not a control mass. It goes like this. And you have this first law memorized. Sometimes they put a summation sign there, but we don't need a summation sign. And sometimes they have other terms here for kinetic and potential terms. But this turbine is not moving, it's bolted down. In fact, if you go to the power plant and look at that turbine, it takes up about, I don't know, 2 average bedrooms in a house. It's big, okay? And the bolts that hold it together, man, I don't know how big they are, but they're about the size of a pumpkin pie, okay? They're big bolts. And you should see the wrench that they have for tightening and loosening those bolts on that turbine. It's a humongous wrench, as you can imagine. If you got bolts about the size of a pumpkin pie, you better have a big wrench. Okay. Minus, don't forget there's another term here. Again, we're going to throw out the kinetic and potential terms. You don't need to worry about potential terms because this turbine is not going uphill or downhill. It's just sitting there. It's bolted down, not moving, not going up or down. Now this here is going to be 0 because it's steady state. The properties don't change with time. They change with location. But see this this 50 degrees Celsius that's at state 1 that's going into the pump. An hour later, it's still 50 degrees Celsius going into the pump. Now coming out of the pump, it's a little bit warmer, not much. Coming out of the pump, it's 50.3 degrees Celsius. Warmed up just a little bit, but not much. But coming out of the pump, it's 50.3 degrees Celsius in the morning, and it's 50.3 degrees Celsius in the afternoon. It doesn't change with time. It changes with location, but not with time. That's a 0. They call it steady state. Now, if you're doing this 1 to 2, that's the pump. It's an adiabat, so that's 0. Now, what I'm going to do is I'm just going to divide through by your mass flow rate, and what you have left is this here. We got rid of those mass flow rates by dividing, and they're equal. And you can solve now. Look at here. We know what both of these are. We have them. They're sitting right here. See them? There's 1 and 2. I'm going to do that. I'm going to subtract those, and I'm going to get this work from 1 to 2. Here goes. You do it with me. Take 1, H1, 209.31. Subtract H2, 214.99. I'm getting the work per mass from 1 to 2 is 5.68 kilojoules per kilogram. Now, how come it's minus? Well, now, just a minute. Well, it's minus.
On the same side, then you add it.
Yeah, because the algebra will tell you that. If you do the algebra correctly, you'll get a minus. How come the work is minus in the pump? How come the work is minus in the pump? Pressure's going up. Look, the pressure's going up from 12 kilopascals to 5,000 kilopascals. That's compression, isn't it? Have I ever told you that compression gives you negative work? Compression is negative work. Expansion is positive work. Well, we got compression. That's how come it's negative. That's where that came from. Now, let me show you another way to get that. Let me, I need a little room here. We'll get rid of this. I'll show you another way to get that. But now, we just figured out how to get that. In fact, I think we've figured out how to get that and that. We're almost done with this 913. But it's taken us an hour. Okay, here's another way. Now, if you did a PV diagram, if you did a PV diagram, we are going from 1 to 2. I just had one and I erased it. I should have kept it. You know what? But going from 1 to 2, it's a isochore. The specific volume stays the same. But see, the work done, I just gave you a little talk about that. I told you what page to read about it. I think it was on page 218. You can go back and read that if you want to. But see, we can get the work of the pump another way. Let's do it that way. Now that's just a rectangle, and the base of it's equal to 0.001012. Well, actually, to be honest, there's a slight lean to the left here. See it? The specific volume was 0.001012, and now it's 0.001008. So why don't we just take an average there? What's the average would be 0.001010, wouldn't it? Does that sound right? I think so. We want the area of that. And what I'm telling you is there's a slight lean to the left there, going from here to here. And the area of this thing, by the way, we should put our units in. That's cubic meters per kilogram. Now the height of this is 5,000 minus 1235. Well, I can't do that in my head. 5,000 minus 1235. I'm getting the height of this thing is 4987.7. Okay, there you go. Now that's kilopascals. I'm running out of room here, and I see if I can squeeze it in there. Kilopascal. Okay, now if you multiply those, you should get the work of the pump per mass. All right, I'm going to do that now. Now what I'm getting, here's where they don't tell you plus or minus. You just got to know that pump, the answer's got to be minus, and I'm getting a minus 5.04 kilojoules per kilogram. Now let's compare that with what we got here. This answer is more accurate in this case because we use the tables. But we use the tables on that too. They're pretty close. I'm getting 5.04. This is 5.68. Yeah, they're off a little bit. I'm not sure I can explain why they're different, but hey, they are a little different. But I'm showing you this to show you there's another way to do it. Okay, so we got that. Now let's do this one. Well, what is this? 2 to 3. That's the boiler. Was there any comment or question before we do the boiler? Okay, nobody said anything. All right. We are going to do the boiler now. Now the boiler is isobaric. If you go down to your kitchen and you boil some water, the pressure you're boiling that water at in the beginning is atmospheric pressure. And the pressure that you boil the water at after 10 minutes is still atmospheric pressure. It hasn't changed any. It's constant pressure. Isobars are funny. They go like this. They go up, they go over, and then they go up. That's just what they do on the TS diagram. Okay, so it's an isobar. Now what are we trying? Oh, we're trying to get the heat transfer. Oh, gee, I shouldn't have erased my first law. But you've seen it so many times before, you know the first term is 0 because it's steady state. The energy in the boiler is not changing with time, unless you're starting the boiler up or shutting it down. Now it can change with time, but when it's in continuous operation all day long, that term is 0. This term is 0. This is the heat transfer rate. It doesn't have any heat transfer. Wait a minute. No, that's wrong. Having another senior moment. What we need is Q from 1 to 2, right? Yeah. We need the, well, maybe I should have the big letters. Maybe I should put in the big letters. This is the 0 here. There is no work. Boilers don't do any work. I just gave you a talk about that, remember? How come on a PV it's straight across, so it's 0 plus m dot h1 minus h2. Well, there you have it. Now we're going to divide through by m dot, and you're going to get this. Q, heat transfer in the boiler, will equal, and you're going to have to flip that. It'll be h2 minus h1. Algebra students, can you handle it? All right, well, let's do it. What's h2 minus h1? Well, there's h2 right there. No. We're doing the boiler. The boiler is going from 2 to 3. We need h2 minus h3, sorry. And we're not doing the heat transfer from 1 to 2. There wasn't any. I was getting mixed up. Sorry about that. We're going from 2 to 3. The boiler goes from 2 to 3. And so what we need is h2 minus h3. Okay, let's do that. h2 how come it's going to come out minus? We can't have minus. Something bad happened.
Mr. Griffin, it's supposed to be H3 minus H2.
Oh. Really? Yeah. I think that was Coy, wasn't it? That was you, wasn't it, Coy?
Yes.
I'll give Coy a thank you point over here. Coy, you're absolutely right. I did bad algebra, but we're okay now. Now help me do H3 minus H2, 34, 3376 minus 214. Did you get the heat transfer per mass in the boiler? 3218.8. Well, by Jove, that's what we got. Look here. We just showed you where that came from. And I gave you a nice talk about boilers, so I hope you were listening. That's 0. 3 to 4 is an adiabat. We know about adiabats. They don't have any heat transfer. Guys, we're almost done here with these boxes. So let's go ahead and do that. It won't hurt us any. This is 3 to 4. That's the turbine. We're going to do the turbine now. Here goes. We're going to do the turbine. And the turbine goes from 2 to 3. Okay. No, that's not right. The turbine goes from 3 to 4. And if you write the first law, I'll write the whole thing out if anybody wants me to, but I know that the first term is 0 because it's steady state and it's no heat transfer. We're assuming adiabatic, in fact, isentropic. And there's your power. And there's your we just threw out the kinetic and potential terms. And if you divide through by your mass flow rate and you don't screw up your algebra, you get the work per mass of the turbine is H3 minus H4. Okay, I'm going to do that. Here goes. H3 minus H4. I get 1197.4. Well, boy, Jove. Kilojoules per kilogram. That's what we got. Yay. Now we have that. This is 0 because, why is that 0? What is that anyway? 4 to 1. That's the condenser. Condensers don't do any work. They condense, but they don't do any work. We have this one last term to fill in, and then we'll have our whole thing filled in. Let's do it. Here we go. Okay, now this is the condenser. It goes from 4 to 1. A condenser is a type of heat exchanger. It's a type of heat exchanger. We didn't work enough heat exchanger problems. I'm sure we did one though together. I remember doing one with you guys. Remember there was something about lake water coming in that was cold. And when we used that to condense the steam, we dumped it back in the lake, but it was hotter. And they didn't want to kill the fish, so they have these two cooling towers. If you go to the power plant, you'll see this cooling tower. They don't want to kill the fish. They try to cool the water off a tad before they dump it back into the river. Okay, condenser, here we go. I hope you guys know what I'm doing. What I'm doing is I'm too lazy to write out this first law. You know how it goes. It goes like this. Blah, 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 blah. You've seen me write it down a dozen times. And I was too lazy to write it, so I just put a 0 because the condenser is a steady state device. This is a keeper though. There's heat transfer out. There's a Q41. There's a heat transfer out. We don't want to hurt any fish, but there's a heat transfer in here, Q23. That's when you're burning your coal. So there's a heat transfer in and out. And this is 0. Condensers don't do any work. And what this will be is H, well, you're going from 4 to 1, so you go H4 minus H1. Divide through by your mass flow rate, and here's what you'll get. Now I need Coy to keep me from goofing this up. I think it'll be H1 minus H4. What about it, Coy? Did I do that right?
Yes, sir.
Good. All right, now do that. Take H1 and subtract H4. Here we go. Okay, well, I got an answer for the heat transfer per mass in the condenser. I got a negative. Well, Shazam, that's what we got. Look at here. That's where that came from. And what does that negative mean? Well, it means that the heat is going out of your cycle and entering the environment. Now, if you add up all the heat transfers, you'll get this. This is the net heat transfer. If you add up all the work per mass, this is the net work per mass. Notice they're equal. If you don't believe me, you add them up. I added them up, that's what I got. The reason for that is, need a little room here to write that. In a cycle, if you add up all the Q's, it's equal to adding up in the cycle all the little W's. In fact, this was the first formulation. They didn't write it like that, but the idea was that the equivalency of work and heat, it was the first formulation of the first law of thermodynamics. Now, we have done 913. Ad nauseum. We probably put some of you to sleep. Any last comments or questions on 914? Okay. Well, we have about, I don't know, 10 minutes left in class. And here's what I want you guys to do for me. In fact, I put it on your homework. You can pull up announcements and it says homework, ta-da. And then you can pull up content and it'll tell you that I want you to do 9106E. So here, we have 10 minutes. We could get a couple of things done. What you're going to do for me is you're going to make a table just like this one. Make me a table just like this one. But now the problem you're going to do for me is 9106E. Now, E stands for Inglés, senor. We've got to learn to work in both SI and Inglés. And what you're going to have up here for homework, what you're going to do is 106E. E stands for English. This is going to be PSI. This is going to be cubic feet per pound mass. This is going to be degrees Fahrenheit. I'll tell you something interesting about the Fahrenheit temperature scale. We'll get back to your homework here in a minute. I've got, I can keep you another 5 or 10 minutes, I bet. You know the Celsius temperature scale, 100 degrees Celsius is boiling. You guys all know that, don't you? And 0 degrees Celsius is freezing. Well, in the Fahrenheit scale, originally they had 100 degrees Fahrenheit and they had 0 degrees Fahrenheit. But the guy that came up with the Fahrenheit scale was a British sea captain. Captain, I don't know his name, Hornblower Q Fahrenheit, whatever. fake that. But the 0 degrees, you know what that was? That was freezing, all right. But it was salt water. See, salt water freezes. Did you know salt water freezes at 0 Fahrenheit, not 32? See, fresh water freezes at 32. You knew that. But it's got to get colder to freeze salt water. That's why if you sprinkle salt on your front walk there when in the wintertime, when it's freezing, it melts that and you don't slip and fall. Because see, it's got to get below 0 to freeze. Isn't that interesting? Now, here's this British sea captain. He originally had 100 Fahrenheit. What do you suppose he had for his 100 Fahrenheit? Does anybody want to take a guess? Got all these wonderful students here. What did Fahrenheit use for his 100 degrees Fahrenheit? It's not boiling seawater. That's not the answer. Okay, you give up. Nobody knows. It was the temperature of his sailors. Now, it turns out that the average, is that how you spell sailor? S-A-I-L-O-R? I think so. It turns out that the average supposedly is 98.6. But we'll forgive him. This was a long time ago. And besides, that's just an average anyway. I'm always lower. I'm always something like 97.9 or something like that. I'm always lower than what I'm supposed to be. All right, well, that's fascinating. And I know you're just enthralled by hearing about the Fahrenheit scale. Now here, we're going to be dealing with BTUs per pound mass. This one's BTUs per pound mass Rankine, and that's supposed to be a Q there. Both of these are going to be BTUs per pound mass. And what we're going to do is we're going to fill in all these boxes. Only we're going to do it for this problem 9106E. You can read about it in content assessments, assignments. You can look it up. But I'll tell you what, we got a few minutes, about 3 minutes I'm going to spend with you. We'll fill in a box or two. Help me find 9106E in your book there. I'm looking, 9106E. Now this is boring, it's tedious. But like I told you, there are boring, tedious things that people have to do. Okay, 9106E, assume a power plant should produce 10,000 BTUs per second of net work. Well, that doesn't go in any of these boxes. You know what that is? That's got to do with this network down here when you get all through. We're not there yet. Steam flows at 800 PSIA. Now that A, I don't know if you remember, that stands for absolute. See, there's absolute and there's gauge. Gauge is what they read in the real world, but absolute is the pressures that we have in our tables. All those pressures in our tables are absolute. They're not gauge. To get, how does it go? Absolute. Now let me write it for you. You probably forgot this. Absolute pressure is equal to atmospheric pressure plus or minus your gauge pressure. Gauge pressure is what they measure in the real world. They have pressure gauge. You have a pressure gauge. You go out to your car, you put it on your tire, it goes, and you look at it. That's a pressure gauge. The absolute pressure is the atmospheric pressure in that case, plus whatever that gauge pressure is. Now, if you have a vacuum, you have to subtract. We studied that a long time ago. I don't put that PSI age. I just go PSI because I know what they're talking about. Now let me read on here. This is 9106E. If you just tuned in, I'm talking about the homework, and you're gonna make a table like this for me. And it says here, steam flows at 800 psi, 900 Fahrenheit to the turbine. Well, I think it's right here. I think state 3 is, hang on, just let me write this down. This is 800 psi, 900 Fahrenheit. Yeah, one of my excellent students wants to talk to me. Go for it. I thought somebody was going to tell me something. Maybe not. To the turbine. Okay, that's going into the turbine. That's at state 3, right? And to the turbine, which has a condenser. The condenser exit is 120 Fahrenheit. Well, you know what? State 1 and state 4 have 120. No, not there. It goes here. It's 120 Fahrenheit, isn't it? State 1 and state 4 both have a 120 Fahrenheit. Okay, I've just put in a few of the numbers. I don't want to spoil your fun. What I want you to do is I want you to fill in all the boxes. That's your homework. I hope you enjoy it. Have fun. Is there any last comments or questions?
Have a good weekend.
Oh, I will.
See you Monday.
I will. I'll see you guys Monday.
Bye.
Bye-bye. So glad you joined us. Now I'm going to click on this end meeting here in just a second.
Mr. Griffin, I have a
Yes.
question.
Yes, go ahead, Coy.
This morning I didn't join the meeting.
Oh yeah, it's recorded. It's recorded. I haven't. My daughter knows how to put it on YouTube, and it will be on YouTube. But
Oh, okay.
it might be tomorrow before she gets it on YouTube.
Okay,
But
thank
you can watch the whole thing, Coy. It's recorded, and you can watch it. Okay?
Thank you.
Yeah.
I think the link's on Blackboard.
Oh gosh, you're talking computer language to me now. All I know is it's available to you guys, and you guys are sharp. And I've talked to students that pull up my videos. They're on YouTube, though. Don't you have to go to YouTube to get them? Those of you that know how to do this, don't you go to YouTube?
Yeah, there's YouTube.
It's YouTube.
Yeah, it's on you.
It's on YouTube. Talk to one of your computer savvy friends, because they're on there. I could get my 10-year-old grandson to come up here and talk to you. Okay. All right. Unless there's somebody else, I'm going to click on end meeting here.
Have a good one, sir.
Okay. 5, 4, 3, 2, 1. Bye-bye. Bye-bye. See you next time.